This is Naresh, working in the assistant professor in EC department. And today's session is question bank discussion on module 4, that is junction field effect transistor. So in this session, we are going to discuss part A and part B questions description, how to attempt these questions from the module 4, that is junction field effect transistor. So we'll see in detail one by one. In the part A, the first question is in nchannel JFET, IDSS means drain to source saturation current is 20 milliamperes and pinch of voltage, that is VP, is minus 6 volts. Then determine the drain current when VGS is minus 3 volts. For this case, first you write in the given specifications, that is drain to source saturation current is 20 milliamperes and the pinch of voltage is minus 6 volts and the VGS is minus 3 volts. Then we know the one relation for this n-channel JFET. The drain current relation is ID is equal to IDSS into 1 minus VGS by VP whole square. So where ID is a drain current, IDSS is drain to source saturation current, VGS is the gate to source voltage, and the VP is the pinch of voltage. So hence, to observe this mathematical relation, the known parameters are the given specifications. IDS is the known, and the VGS is also known parameter, VP is also known parameter. By using this one to solve this drain, means IDSS is 20 milliamps, 20 into 10 power minus 3 minus 1 minus VGS is, so this is 3 volts minus 3, then by VP is minus 6, that is whole square. To solve this one, then we can observe this drain current. And the second one is determine the transconductance of a JFET if its amplification factor is 96 and the drain resistance is 32 kilo ohms. So here we need to find out the transconductance. So, and based on the given specifications, that is the amplification factor is 96 and the drain resistance is 32 kilo. And for this question, we know there's some relations between the characteristics of the JFET. We have the two types of the characteristics. One is drain characteristics and transfer characteristics. From this drain and transfer characteristics, we have one relation, that is mu is equal to GM times of the RT, where mu is amplification factor and the GM is a transconductance and RT is the internal drain resistance. So hence, for this given specification, the given factors are mu amplification factor is 96 and the drain resistance is 32 kilo ohms. The unknown parameter is the transconductance we need to calculate. So hence, use this formula, mu is equal to GM times of RD. So from this, if you want to determine this transconductance, the transconductance mu GM is equal to mu by RD. So here substitute the given values, amplification factor and drain resistance. So here the amplification factor is 96 and the drain resistance is 32 kilo ohms. So means 32 into 10 power 3. Then you can solve this ratio, it gives a GM value. We'll see another question. A JFET has parameters of VGS of is minus 20 volts and IDSS is 12 milliamperes. Determine the drain current for the device using VGS is equal to 0 volts. So for this case, first to identify the given specifications, they given the VGS of the VGS of is minus 20 volts, and drain to source saturation current is IDSS is 12 milliamperes. Then we need to calculate the drain current when the VGS is 0 volts. And we know that from the characteristics of JFET as a transfer and drain characteristics, we derive the drain current expression is ID is equal to IDSS into 1 minus VGS by VP whole square. Now we can substitute now the given specifications in a problem. They mentioning that the drain to source saturation current is 12 milliamperes. Hence, this is IDSS is 12 milliamperes, means 12 into 10 to the power of minus 3. Then 1 minus VGS is 0. VGS is 0, and VP value is means that if you observe the transfer characteristics from the JFET, and the transfer characteristics are drawn between VGS and versus drain current. Hence, the x-axis I represented as the VGS, y-axis I represented the drain. If you recall this transfer characteristics of the JFET, so we know that when VGS is a 0, then the drain current is a maximum. That maximum here it is represented as IDSS. When a VGS is decreased from the 0, then the drain current is also decreasing towards minimum. At which point the drain current becomes a 0, that point here it is called as VGS of, it is also called as pinch of voltage. Hence, from this given specifications, we can assume that the VGS of that is equal to pinch of voltage, that is VP. So hence, now I'm going to substitute VP that is equal to VGS of that is minus 20, that is whole square. So 0 by something is a 0, 1 minus 0 means 1, 1 square is 1. So hence, the drain current is 12 into 10 to the power of minus 3. Hence, the drain current is 12 milliamperes. Now, if you want to verify in the theoretical concepts from the transfer characteristics, if you know this one, when we plotted like this, when VGS is 0, the drain current is a maximum. The drain current is approximately equal to drain to source saturation current. So that is the reason. Here also, we are observing the same. When VGS is a 0, the drain current is equal to drain to source saturation current. That is here 12 milliamperes. Now we'll see another question. An n-channel JFET has the drain to source saturation current is 8 milliamperes and a pinch of voltage is minus 5 volts. Determine the minimum value of drain to source voltage for pinch of region, and the drain current IDS for VGS is minus 2 volts in the pinch of region. So for this case, we need to find out the minimum value of the VDS for a pinch of region as well as the drain current for when VGS is minus 2 volts. So for this case, first we need to calculate the minimum value of VDS for VGS. So hence, VDS minimum that is equal to, can write VGS minus VP. From the given problem, they given that VGS is minus 2 volts and a pinch of voltage is minus 5. Hence, from this, the VDS minimum, it becomes 3 volts. So we know that the generalized expression from the n-channel JFET, the drain to source, this is IDS, or you can also write ID means that why I'm using the drain IDS means the drain current is flowing from drain to source, and that is indication the current is flowing from drain to source, or it is also called the drain current ID. So we know that IDS is into 1 minus VGS by VP volts. So from the given specifications, the IDSS is given as 8 milliamperes. Hence here So IDS is 8 milliamperes. 8 into 10 power minus 3 means 8 into 10 power minus 3 into 1 minus. So that is VGS is minus 2 and VP is minus 5. That is the whole square. Then it gives that a ratio is 2.88 milliamperes. So hence the drain to source or drain current that is equal to 2.88 milliamperes. Now from this, now we need to calculate. So so we identified VDS minimum as well as here IDS minimum. So VDS minimum is, for this case, the minimum value of VDS is, that is 3 volts, and the minimum value of drain current IDS is, that is 2.88 milliamperes. You see another problem. A JFET has the parameters of VGS of with a minus 10 volts and IDS is 6 milliamperes. Determine the drain current for the device using VGS is 0 volts. First write down the given specifications. So VGS off is minus 10 volts and drain to source saturation current is 6 milliamperes and the VGS is 0. Now we need to calculate the drain current. So we know that from the JFET characteristics, the drain current is represented as ID or IDS, drain to source saturation current, that is equal to IDSS means drain to source saturation. IDSS means drain to source saturation current into 1 minus VGS by VP whole square. So now where we know that IDSS is a known parameter, VGS is a non-zero, then first we need to identify the VP. To understand or to identify this pinch of voltage, just can recall the transfer characteristics of the JFET. So to identify this transfer characteristic JFET, the transfer characteristics are drawn between VGS versus the drain current. So means in the x-axis I'm going to represent with the VGS, but from the JFET construction, to control the drain current, the gate should be reverse bias. So that is the reason VGS is a reverse bias, and the y-axis is represented as drain current. When the VGS is represented as 0 and it offers a maximum current, that is represented as drain to source saturation current. When the VGS is decreased from the 0, so what happens, drain current is also decreasing, and at certain stage, at certain voltage, your drain current becomes 0. At this point, this voltage is called as a VGS off, that is also called as a pinch of voltage. So hence, from the given specifications, the VGS off, that is equal to a pinch of voltage, that is VP, means that is equal to 10 volts. Now we can substitute all these specifications to solve this drain current in this relation. So that is ID is equal to IDS is equal to IDSS means 6 milliamperes means 6 into 10 to the power of minus 3, 1 minus VGS is a 0, VP is minus 10 volts, that is whole square. So hence ID equal to, so this is 6 into 10 to the power of minus 3, 1 minus 0 by something is 0. So this is 1 square is a 1. Hence, the ID is equal to 6 into 10 to the power of minus 3 amperes. So ID is equal to 6 milliamperes. Now we'll see another problem. A JFET amplifier with a voltage divided by a circuit has the following parameters, that is VP is minus 2 volts, IDSS is 4 milliamperes, the drain resistance, external drain resistance is 910 ohms, source resistance is 3 kilo ohms, R1 is 12 mega ohms, R2 is 8.57 mega ohms, and the VD is 24 volts. Solve the value of drain current ID at the operating point. Verify whether the FET will operate in the pinch off region or not. So means we are going to use a voltage divided by a circuit, and the circuit contains the specifications. They mentioned like the pinch off voltage is -2 volts, and the drain to source saturation current is, that is nothing, the IDSS is 4 milliamperes, and a drain is a biased with a resistance that is 910 ohms, and here the source is biased with 3 kilo ohms, and there using this voltage divided by network, hence the R1 R2 values are 12 mega ohms and 8.57 mega ohms respectively. Then it is a bias with 24 volts. Now we need to find out the value of drain current at the operating point. For this operating point, either it should be operating in the pinch off region or not, we should verify. So for this case, we know that from the voltage divided network, the gate to source volt means the gate voltage is represented as R2 by R1 plus times of VDD. So then you can substitute the R1 values and R2 values and the VDD voltage. Then the gate means like this. So input side, it is connected to a gate voltage, and this is R2, R1. It is biased with the VDD. Now we need to calculate this VGG. So hence, so how to find out this one means VDD minus VGG by R1 plus VGG minus 0 by R2, that is equal to 0. So from that, this you can write this is VDD by R1 minus VGG by R1 plus VGG by R2. So then you can from this node, just a minute. So if you want to apply from this node, you can write from this node. So means that is VGG minus VDD by R1 plus VDD minus 0 by, this is 0 node, to the R2, that is equal to 0. So hence VGG by R1 minus VDD by R1 plus VGG by R2, that is equal to 0. So from this, if the VGG is the common, this is 1 by R1 plus 1 by R2, that is equal to VDD by R1. Thus you can take the LCM and simplify this equation. That becomes VGG equal to VDD times the R2 by R1 plus R2. So hence, so here you substitute the VDD value, R1 and R2 values to observe, and that Thevenin equivalent voltage across the gate, that is 10 volts. And again, from this JFET, we know that the drain current is represented as IDSS into 1 minus VGS by VP whole square. So then we can substitute this one. IDSS is IDSS minus VGG, means if you are adding this VGS, the name itself, here there is no VG, as earlier we had. So means we can write the potential difference between gate and source, VG minus VS. So again, from this voltage divided network means gate, and this is the drain and the source. The source is biased with a resistance, that is RS. So hence the voltage drop across this RS hence is represented as VS. Hence we can write this one VG. So the drain current is flowing through the source, hence we can write IS into RS. So generally we know that from the transistor construction, the source drain current is approximately equal to source current, hence this is VG minus ID times of RS. So, and that is the reason VG means I represented as VGG minus ID times of RS. So hence this VGS is replaced with VGG minus ID times of RS by whole square. Now we can substitute, express all those values. So in the problem, the IDSS they given that 4 milliamperes. So hence I am substituting this 4 milliamperes into 1 minus. So VGG value we observe 10 volts. So this is 10 minus ID is the unknown parameter, and RS value is a 3 kilo ohms. So it means this kilo ohms and a milliamps is the get cancelled there by VP, that is minus. So you can solve this ratio, then we can get this ID value to two different cases, means that is ID. So this is the characteristic equation, second order equation is there. So from this second order characteristic equation, then find out the roots, and for this, the root from the roots, the drain current is 3.39 milliamperes or 4.72 milliamperes. So then we need to find out at which then the transistor could be operated in a pinch of freezing. So for this case, we need to identify how much. So here you have you observe the Q point. So the drain to source current, the problem specification, the drain to source saturation current is given as 4 milliamp. Means we should take the value should be always greater than of this one. So then, and this, so that is the reason. So we taken as this value is supported to satisfy this 4 milliamperes. Then now we need to find out the Q, VGS Q. So means again just now we observed that VGS, VGT minus ID into RS. So hence I substitute the Q point at Q. So 10 minus IDQ, we observe that 3.39 into 10 to the power of minus 3, and RS is 3 into 10 power 3. Then we use that minus. Then again, so we can substitute this one in terms of VDSQ. So to observe this output side means this is, let us take drain and the source. We have the RD resistance. This is biased with VDD and the source is biased with RS. So here, if you want to find out this VDS, now you can write this is VDD minus. Otherwise, you know the chemical equation VDD is equal to ID into RD plus VDS plus ID into RS. So then that means that VDD is equal to, if ID is a common, we have RD plus RS plus VDS. From this, we need to find out this VDS. VDS is equal to VDD minus ID times of RD plus RS. So the same equation I used here. So in the place of ID, I use the IDQ. Now we can substitute VDD values and IDQ, RD and RS values to absorb this VDSQ value. And similarly, we need to find out we drain to gate Q point. So that is means nothing but the potential difference between drain to source and the gate to Q voltage. Then the VDGQ is 10.915 volts. Now it should be greater than of 2 volts, hence the FET should be. So actually they've given the pinch of voltage is 2 volts, but we observe that there is 10.95 volts, hence the FET should be in a pinch of region. Now another problem is a voltage divider bias is provided to n-channel JFET circuit as shown in figure. To establish the drain to source saturation current is 10 milliamperes and a pinch of voltage, that is Vp, is a minus 3.5 volts. R1 and R2 together 20 kilo ohms, and the drain current is 5 milliamperes and the drain to source is voltage is 5 volts. Solve the R1, R2 and R2. So here they are given the how much current we are going to generate by using the circuit. So then we need to find out the biasing resistances R1, R2 and RT. For the given specifications means to provide the drain to source saturation current is 10 milliamperes and the drain current is 5 milliamperes and drain to source voltage is 5 volts. So again from that characteristic, then from that JFET principle, we know that the drain current expression is ID is equal to IDSS into 1 minus VGS by VP whole square. Here the unknown parameter is only the VGS, and substitute IDSS value, VP value and ID value, then can determine this VGS. That VGS is, so what is ID value in the given problem? ID is 5 milliamperes, and 5 into 10 to the power of minus 3, that is equal to IDSS is 10 milliamperes. So 10 into 10 to the power of minus 3, 1 minus VGS is the known parameter, and the VP value is, so the given the VP value is minus 3.5 volts. So this is whole square. Then from this you can solve this VGS, that VGS is equal to minus 1.008 volts. Now we need to find out the voltage drop across the source. We know that that is equal to ID times of RS minus. So means we need to find out this one, the voltage drop across the source. So VDD equal to, so we can write, so if you observe this one, the circuit, the drain is, and again this is source. So here we need to find out here for this case. Let us take this is a VD. So here we need to find out how much voltage drop Vs is across. Mean that is the reason we can write directly that is ID. Here the how much which current is the flow source current. But generally we know that ID is approximately equal to Is. Hence we can write ID times of Rs. And between then we need to subtract from this VD1. So that is the reason. Here I use this one. So ID times of Rs minus 5. You can substitute ID value and Rs value. Then we can observe this source voltage. Then the gate voltage is like that VGS is equal, means between this one gate we need to find out this VGS. So we know that VGS is equal to VG minus your Vs. So from this we can write VG is equal to VGS plus Vs. So hence I represented here the gate voltage is VGS plus Vs. Already we observed VGS and Vs is observed, and you can substitute these two values to observe how much gate voltage is required, that is minus 3.508 voltage. So, and from the voltage divided network, we have that one based on the gate voltage, we have this voltage division rule R2 by R1 plus R2 times of VDD. So, N that should be taken from minus your drain to source voltage VDS. So, hence R2 by R1 plus R2, this is VDD here, 10 volts minus this is VDS voltage is minus 1. So you can substitute that one, can identify the relation between R1 and R2, then you can observe this R2 values and R1 values. Now we need to find out drain to source voltage. So that is from the circuit. So we know that one drain to source voltage is VDS minus, means in this network. So we need to find out this. So ID means we need to find out drain to source voltage, total drain to source voltage. This is VD5 minus ID times of RD minus ID times of RS. So hence you can substitute the same value, 5 minus ID times of RD minus ID times of RC minus drain to source voltage is VDS is minus 5 volts. Hence, so then you can substitute here. Then we know that VDS is already observed. Now ID is observed. Now we need to calculate RD value here. Then so this is VDS is a 10 minus VDS is a 5. Then ID minus ID into RS by ID. Then you can solve this ratio. It gives that RD is equal to 0.5 kilo ohms. And again from that we know that the pinch of voltage VGS minus VP here, that is minus 1.24 minus VP is 3.5. That gives that how much gate voltage is required here. Now coming to the part B, some theoretical questions. Translate the JFET with a low frequency model. So we know that based on the transfer and drain characteristics, we represented is the ID is represented as GM times of VGS plus 1 by RD times of VDS. By using this mathematical relation, you draw this low frequency model. So input side this is VGS, and output side, let's say this is the drain terminal, common terminal source, input is the gate, and here we are applying the VI. So ID is represented as the current source is GM times of VDS plus 1 by this is RD. So 1, and between this drain and source we are observing the VDS. Hence now we are going to find out this is V0, and here the current is drain. Now we can explain this operation here. With the neat sketches, explain the construction, principle of operation, and the characteristics of n-channel JFET. So for this case, first you draw the n-channel JFET. To identify this n-channel JFET, let us take n-type semiconductor bar. So one end is connected with the metal, that is drain, another end is the metal is the source. And opposite sides, we need to diffuse this a heavily doped p-type materials. Internally, these two are shorted. Externally, it is connected to gate terminal. So, based on this, you should explain how the N-channel JFET is constructed. Then, to identify this operation, we need to apply some biasing voltages between drain and the source. And based on this construction, the source and the drain is made up with N-type material. So hence, the source contain the charge carriers, that is, majority charge carriers are electrons. To diffuse these charge carriers, we need to apply some amount of the force externally. Hence, drain is biased with the positive pole of the battery and the source is biased with the negative pole of the battery. And this biasing is represented as a VDD. Hence, the source is contain the majority charge carriers are electrons. Hence, we need to apply the negative force. When you apply the negative force, the charge carriers are diffused from the source to drain to allow the drain current. Hence, the drain current flows from the drain to source. Then, if you want to control this drain current, then we need to apply a reverse voltage across the gate terminal to control the flow of drain current. This biasing is represented as VD. So then you can explain the characteristics. So transfer characteristics and drain characteristics. Then if I'll explain the drain characteristic drawn between drain to source voltage versus drain current by keeping gate to source voltage is constant. Similarly, while explaining the transfer characteristics drawn between gate to source voltage versus drain current by keeping drain to source voltage is constant. If you want, you can report the construction and principal operation of N-channel JFET video session. Now, similar to that, explain the construction and operation of P-channel JFET. So, first you should draw this the construction part. So, means we need to consider a P-channel. This is the channel is a material is a P-channel. So hence the source and the drain is doped with the P channel. And opposite now we need to diffuse with a heavily doped N plus material. Internal these two are shorted. It is connected as a gate. Now again the principle is the same. Here the biasing is to diffuse the charge carriers. In a JFET, the conduction depends upon only the majority charge carriers. So based on this P channel, the source contain the majority charge carriers are holes. To diffuse these holes, we need to apply the positive energy. Hence, source is biased with the positive pole of the battery and drain is biased with the negative pole of the battery. Then to control this one, again here we need to apply the reverse biasing voltage to control the flow of drain current. Then explain the operation, how the drain current is allowed and what type of biasing voltage is here. Then if you want to refer, you can refer the videos of the construction and operation of N-channel and the P-channel JFET link. And summarize the enhancement and depletion MOSFET. And here the MOSFET means a metal oxide semiconductor field effect transistor. So in this also we have the two types of the MOSFETs here. One is enhancement, another one is depletion. So first you explain how to fabricate this, how to construct the MOSFET. For this construction, first we need to take one substrate. So the substrate is, if the substrate is a P-type, we need to take N-type materials for the drain and the source. If the substrate is the N-type, we need to take the P-type metals like for the source and the drain. Then we need to diffuse the source and drain. Then it places the insulator, that is silicon dioxide. Then places the one metal. The metal is connected to gate. Then the only the difference is in enhancement and depletion. In enhancement, there is no channel is established while constructing the configuration transistor. But in the depletion MOSFET, while constructing the transistor, it establishes the channel. But in enhancement, while based on the biasing voltages, it creates a channel between the drain and the source. Now determine the expression for the pinch of voltage Vp in the case of N-channel JFET. So for this case, first you explain the operation of N-channel JFET operation, then derive the expression for pinch of voltage by using the mathematical derivation like ID is equal to IDSS into 1 minus VGS by Vp whole square. If you want, you can refer this the operation of n-channel JFET, and there I derive this pinch of voltage. Then explain the voltage divider biasing in field effect transistor. So for this case, you can consider the JFET. So means the JFET means it is gate, drain, and a source. So we need to use the voltage divider biasing circuit. First, to draw the voltage divider by circuit. This voltage divider by circuit contains the two resistances on the input side, R1 and R2. So this R2 is connected, and drain is biased with RD, and these two are connected with the VDD, and the source is connected with the RS. It should be connected to ground. And internally, this potential difference between gate to source is VDS, and here the potential difference between drain to source is VDS. Then explain the operation, how it is, why it is called as a voltage divider biasing, how it maintains the stabilization Q point. Then identify the expressions for gate current and drain current, as well as the source current, as well as identify the drain to source voltage and gate to source voltage. If you want, you can refer the voltage divider biasing of JFET concept video session. Then demonstrate the fixed bias operation using the field effect transistor. So for this case, so first you draw the circuit for field effect transistor using the fixed bias operation. So means that, so in this case, let us take a JFET, and you can take n-channel JFET or p-channel JFET. So if I take, and this is the drain and the source, drain is a bias with a drain resistance RD, and this is VDD. And here this is, let us take RG, it is biased with a constant voltage source, and source should be connected to, let us take, this is VG. So this type of biasing is belongs to fixed bias. Then you can explain this operation and derive the mathematical relations for VDS and drain current, and explain the construction and operation of n-channel MOSFET in depletion mode with the help of characteristics. So n-channel depletion mode means, so we need to take a p-type substrate, then we need to diffuse the metal. So this is called as a source and a drain. This is channel, and now we need to place the insulator, that is silicon dioxide. Then place on top metal. This is the conducting plate. This is connected to gate. Now this is drain and the source. Now we need to apply the biasing voltage between this drain and the source. Hence, drain is a bias with the positive of the battery with respect to the source. And then explain how, with respect to the biasing voltage, how the drain current is flows by using this depletion MOSFET. And similarly, then you can apply the gate to source voltage. So here the gate should be biased with reverse bias with respect to source. Then you can explain how the drain current is controlled by the variation of this drain to source voltage and gate to source voltage with respect to the characteristics. We have the two types of the characteristics. Should explain with the drain characteristics and transfer characteristics. If you want, you can refer the MOSFET construction and operation with the characteristics video session. So here, same thing, you can explain the construction principle of enhancement of. But only the difference is, in a depletion type, we observe that while the construction, the channel is established between source and drain. But here there is no channel between the source and the drain. Means, so let us say this is a p-type substrate, and this is diffusing the metal source. It is called as the source. And let us take, this is drain, and this is insulating silicon dioxide. Then place the one metal. The metal is connected to gate, but here there is no channel. But you should explain how the channel is induced while you're applying the biasing voltages between drain to source as well as the gate to source. Then again also explain how the drain current is closed and how the drain current is controlled by the variation of VGS and VDS with the help of characteristics, that is drain characteristics and transfer characteristics. And similarly, so just now we discussed that how to write the for a n channel depletion type. But here the p channel means just you change the substrate and you can change the source and the drain materials. Then you can explain with biasing voltages for drain characteristics and transfer characteristics. And here you should derive the expression for JFET drain current. Means we should observe this one. ID is equal to IDSS into 1 minus VGS by VP was okay. If you want, you can refer the JFET drain current equation video session. Then demonstrate the fixed bias operation using the MOSFET. So first you can draw the MOSFET with a fixed bias, then explain the operation for this fixed bias operation. Then by using this fixed bias MOSFET configuration, you should derive this drain current and drain to source voltage and the gate to source voltage. And similar to that here, explain the voltage divider biasing in MOSFET. First you draw the voltage divider circuit for MOSFET, then explain the operation, means how the biasing voltages, what type of the biasing voltages are required, and what happens if the biasing voltages are changes, and how the drain current is changes here. And then derive the expressions for gate voltage and gate to source voltage, drain to source voltage, and drain current by using this voltage divider biasing for MOSFET. So up to this point in this session, we observed the part A and part B question discussions from the module 4, that is JFET junction field effect transistor. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.